When you think of electricity, what's the first thing that comes to mind? Is this something as simple as a light bulb, or a toaster, TV, or electric car? Or is this even a good question to be asking these days? See, that's the thing. Most of us go through our daily lives and we interact with technology that just works. And we don't really need to know why it works the way it works. But I think sometimes it's okay to revert back to our 3-year-old selves and ask why. Why does it work this way, or how does it work this way? A lot of us have kind of just stopped doing that. In this video series, I want to take you on a journey from simple circuits to complex electronics. And whether you know nothing about electricity or you're an expert in the field, there's something here for you. So let's take a really good look at how this stuff works and keep asking why it is the way it is. Let's go. To start off this project, I wanted to talk to some experts about the importance of learning electrical fundamentals. These guys do this every day, and this is what they had to say.
I am a firm believer that you should always learn at least a general amount of everything that you're working or interacting with. So I mostly write software, but I have to know how 120 volts and 24 volts and all this is going to interact, and what's safe and what's not too.
Not only is it going to get more fun, but it's going to get more fun if you have a good understanding of the fundamentals. If you get to like more advanced concepts and you don't have a good understanding of the fundamentals, then you're going to get frustrated because you can't tie everything together.
Alright, so let's get started by building the simplest circuit that I could think of. And for that, we're going to need a power source. In this case, we'll use this AA battery. Then we also need something to do work for us. And that's where this little light bulb comes in. Finally, we need something to put the circuit together to conduct the electricity, so we'll use these conductors or wires. And you can probably already tell what's going to happen. Maybe some of you have done this as kids. But when you connect everything the right way, you make the light bulb glow. And I probably surprised nobody by doing that, but imagine how revolutionary that would have been like 200 years ago. I think most of us have some intuition that electricity flows through the wire and it powers up the light, and maybe you also know that then it keeps flowing and it flows back to the battery. But what does that even mean in the first place? What is electricity? See, we need to take a deeper look at the fundamentals and ask why and how a little bit more, so that when we get to more complex components like transistors, for example, we have a better idea of what's going on. So let's take a quick look at some of the science. This is an atom, a copper atom to be exact. In the center or nucleus we have protons and neutrons, the heavy stuff that give atoms the vast majority of their mass. On the outside live the electrons, these extremely light elemental particles that spin around the nucleus. This is a really simplified and not to scale representation of what atoms actually look like. But in reality, the electrons move so fast that they would look more like a cloud. I would say it's too hard to explain the behavior of these subatomic particles by looking at a cloud, so textbooks dumb it down a little so our little brains can comprehend what we're looking at, and that's okay. Throughout this series, we'll be taking shortcuts and simplifying as well, and I'll make sure to let you know when we do so. Okay, so if these electrons are moving so fast, what's keeping them from just flinging out of the atom? The answer is electrical attraction. The one key property of protons and electrons is that protons are positively charged and electrons are negatively charged by the exact same amount. Much like magnets here, opposites attract. So if we put a proton and electron right next to each other, they would come together. But if we give the electron a little bit of energy in the form of motion or kinetic energy, a balance will be achieved. It may even help to think about our own solar system, where the planets are bound by gravity and held in orbit by their speed around the sun. Atoms similarly achieve a balance between the two forces, the electrical attraction between the particles and the electron speed. Like the solar system, atoms contain electrons at different distances from the nucleus, arranged in groups called shells. Copper here has an interesting property in that the outermost shell or valence shell only has one electron in it, and this matters. Let's see why. Take two electrons in isolation. they're both negatively charged, right? So they repel one another. If one was moving towards the other, that repelling force would cause the other to also move. On a much larger scale, you could also do this with magnets. And this concept becomes a bit more intuitive, I think. So, going back to our copper atom, our valence electron is pretty vulnerable. It's spinning around and minding its own business, but if another electron comes along with any speed, it could repel the valence electron enough to bump it out of orbit and take its place. Man, what a bummer, this electron has no home now, and we could even call it a free electron as it's not bound to any atom. But wait, there's another copper atom over there, and it's heading straight for it. And the whole process happens again in a sort of chain reaction. For simplicity now, we'll just call these electrons that jump around free electrons, and the rest of the atom the copper ion. What makes it an ion is the fact that if you leave one electron out, the core is slightly positively charged. So if we zoom out a bit, we could see that the ions form a structure or lattice with free electrons mostly staying bound to their ions. But as soon as we introduce more electrons, they sort of push the free electrons into the chain reaction, and this push is called EMF, or electromotive force. In other words, electricity. I think it's normal for people to think of electricity as this thing that moves through wires at the speed of light, and yes, electrons on their own do move very quickly, but the speed of electricity through a wire has a lot more to do with the chain reaction than the speed of any single electron. So a neat illustration of this concept is this little toy that my daughter has, where if you move a gear on one side, all the other gears affect each other, and you end up moving this gear that's the farthest away. And of course, I only have to move this just a little bit for all this distance to be covered and the effect to reach this side. And that's kind of how electrons work. As they're excited and they're jumping around, that energy is a bit of a chain reaction where it makes its way down the entire length of the conductor, even though the electron doesn't have to travel that far. This is all possible because of the fact that some materials, like copper, have very vulnerable outermost electrons. And this property is called conductivity. Another good conductor is aluminum. It has 3 outermost electrons, which is actually the limit of what we label as a conductor. On the flip side, insulators are atoms with many outermost electrons, 5 or more. These electrons are not very susceptible to change. Meaning, if we shoot an insulator such as neon with a fast-moving electron, it's just going to bounce off and create some movement or heat on the whole atom. No chain reaction to speak of here. In the middle lie semiconductors with 4 valence electrons, and they're a bit special, showing some mixed properties. This really matters because we can take advantage of these elemental properties to conduct or insulate electricity as we need it. For example, there's electricity flowing to this light, but I can hold onto this wire and not get shocked because there's an insulating layer of plastic around the copper conductor that's in the center. You can see then that the atomic properties of these elements carry over into larger scales, allowing us to control whether the electricity flows or doesn't flow. So the next question is, how do we even get electricity to flow in the first place? In nature, there are very few examples of electricity visually flowing. It took a long time for humanity to really come to terms with how to replicate this flow. 2,500 years ago, this would have made you famous. It was Thales of Miletus who first recorded this phenomenon around 500 BC, and we now know it as static electricity. He didn't actually do it with balloons, but the concept is the same. The rubbing transfers electrons from your hair to the balloon, making the balloon negatively charged compared to its surroundings. When the balloon is placed near the wall, then they attract one another. To the balloon, the wall appears positive, even though from a different vantage point we might say it's neutral. This illustrates that charges are always relative. With this in mind, it took another 2,000 years for humans to produce flowing electricity. In 1799, Alessandro Volta published his findings on what was later coined as the voltaic pile, basically the world's first battery. Volta realized that he could use chemistry to create a charge imbalance that would force electrons to move. We won't really get into the nitty-gritty here, but in basic terms, he found out that if he placed copper and zinc close to each other with a layer of water in between, the zinc would release electrons and the copper would absorb them. This would create an imbalance of charges, or voltage, and if he stacked this configuration into a pile, the effect would become stronger, making one end of the pile very negative with a surplus of electrons, and the other equally positive with what you might call missing electrons or electron holes. When he placed a conductor between these two ends of the pile, the electrons would try to flow from the negatively charged end to the positive end in order to restore balance, producing electromotive force or flow. And here we need to pause and clarify a couple things. Remember, there's already free electrons in the conductor before it's connected to the battery. So as these new electrons push out of the battery, they create a chain reaction which moves all the electrons. At this scale, thinking of electrons just zooming through the wire seems intuitive, but in reality, their average speed through the wire is way, way slower than you might think. And I mean, something as slow as a 1/4 inch per minute. So it would take several minutes for an electron leaving the battery to actually reach the other side. I know that's not intuitive, but if we look at a single electron, it bounces around extremely quickly. However, its average velocity or drift velocity along the conductor is still relatively slow. Even at this slow speed though, there are billions of electrons flowing, so the effect is meaningful. Finally, I want to address the fact that these electrons are flowing from negative to positive. This is what actually happens in circuits, and we refer to this method of analysis as electron flow. But you might be more used to thinking in terms of conventional current, which flows from positive to negative. What is conventional current then? When Benjamin Franklin was experimenting with charges way back when, he arbitrarily assigned labels to these charges, and thus we began using this convention. It's a mistake, really. Nothing really flows from positive to negative. But we can't really blame Mr. Franklin, as we didn't even know what an electron was until 1897. Today, we're still using conventional flow for most circuit analysis because most of the time, the direction of flow makes no difference. And so far, we've only been looking at direct current, or DC, which is current that flows steadily in one direction, like what you get from a battery. But there's also alternating current, or AC, like what flows through the wires in your house, in which the current constantly changes direction. In this video, we'll stick mostly with DC, but all the concepts really that you'll see in the next few chapters do apply to both DC and AC. Okay, so you'd think the logical next step would be to talk about Thomas Edison and how he invented the light bulb, giving the battery something to power, except no. Thomas Edison did not really invent the light bulb in 1879 as some textbooks would have you think. Let's go back to Volta's battery to see what he did with it. When Volta put a bare copper wire across the two ends of the battery, the wire lit up. This was the first accidental invention of incandescent lighting. But it didn't glow for very long, as the copper wire would burn up with the heat. Volta made all his findings public, so just a couple of years later, Humphrey Davy invented the arc light, which is basically two carbon rods with a literal continuous spark crossing between them. This lasted longer, slightly longer, and it was extremely bright, but it also consumed an enormous amount of energy as well as being noisy. Finally, in 1850, Joseph Swan began experimenting with filaments, which are a piece of conductor specifically designed to glow when electricity flows through it. He also surrounded the filament in glass in a vacuum, and due to less contact with the air, the filament would oxidize or rust less and thus last longer. But the filament still didn't last long enough to make the light practical, and the reason was due to resistance, or lack thereof. Swan's filament allowed for a large amount of electricity to pass through it, so we could say its resistance to current flow was low. Thomas Edison then came in and said, okay, if I make the same kind of light bulb but with a filament that has a higher resistance, it won't allow for as much current to flow through it, and it'll last a lot longer. And that's exactly what he did. He created the first practical light bulb design, founded the Edison Company, and the rest is history. So to close off this chapter, I think it's only appropriate to finish off the science that we started with. Why does a light bulb glow when we hook it up to a battery? First, the battery creates an electric imbalance, with a surplus of electrons on one side and a lack of electrons on the other. Then we go to the copper cables, which we know are good conductors, so as soon as they're connected, the surplus electrons from the battery try to flow to the other side, and as they do so, they push and bump into the valence electrons and the chain reaction starts. Meanwhile, the light has a filament which restricts the flow of electrons, So they bump into the atom cores or ions repeatedly, causing them to move quickly. Most of this energy is dissipated to the surroundings in the form of heat, but about 10% of the energy is radiated in the form of light. The electrons continue to do this until the battery imbalance decreases and the light gradually turns off. Of course, not every circuit is battery powered, and most circuits are more complex than a single light. But armed with these basic tools, we can continue to demystify this wonderful phenomenon that's proven so useful in daily life. When it comes to electricity, if you're a beginner, water can be your best friend. Or even if you're not a beginner. But what is electricity to you?
I don't know how many people refer to it this way, but I kind of like to think of it as water in a pipe, really. A lot of the same concepts exist. It just could move really, really fast.
Here we have a hose and we turn the water on. The hose is unrestricted, so the water flows quickly, determined by the pressure coming out of the spigot. But now we put a kink or restriction on the hose, and what happens? The pressure coming out of the spigot is the same, but because of the restriction, the resulting water flow will drop. How much the flow drops has to do with how much of a restriction we have. We could easily put this into an equation where the resulting flow is a function of the water pressure coming out of the spigot divided by the restriction. Something very similar happens in circuits. Let's go back to our simple circuit consisting of a battery, wires, and a resistive load, the light. The amount of electrons flowing through the wires is dependent on how much pressure or voltage the battery will exert on the circuit, and how much resistance the light provides. Again here, we can put this into an equation where flow equals the voltage divided by the resistance of the light. In electrical terms, we usually call flow current. This equation is referred to as Ohm's law, published by George Ohm in 1827, and it establishes a beautifully simple relationship between the three parameters. As long as you know any two of them, you can always find the third by rearranging the equation. The units for these parameters are volts for voltage, amperes or amps for current, and ohms for resistance. So let's use this law on this light bulb, which says it's rated for 2.5 volts and 0.3 amps, to find out its resistance. When we plug the numbers in, we get about 8.3 ohms. So let's take these numbers and compare them to what we'd actually see in the real world. What I have here is this nice little power supply, which I've set to 2.5 volts. And so we're always going to get the 2.5 volts that we're looking for here. And I have this little light bulb. I've just put it in a little holder to make things slightly easier. And you can see when I plug it in, it shines nice and bright. And our amp draw is actually 0.29 amps, which is really close to that 0.3 amps that the light bulb said it would take. Now, in the field, you're not going to have a nice unit like this that's going to automatically tell you the voltage output and the current through your circuit. So you're going to have to use different tools to measure this. For example, here's a voltmeter designed specifically to measure voltage across a load. And the way you hook it up is you put it around the load. And here you can see it's reading about 2.5 volts, which is correct. Same thing with current. You can have a tool specifically designed for measuring current, like this ammeter. The other one was a voltmeter. This one's an ammeter. But we have to hook it up slightly differently. This has to actually become a part of the circuit. So I'll hook it up like this. See, we've got just between 0.2 and 0.3 amps. And if you think about it, it wouldn't be very practical to carry in the field an ammeter, a voltmeter, later on maybe an ohm meter. So we don't really use these in real life. What we actually use is something called a multimeter. And it's called a multimeter because it's got multiple functions. The big three are being an ammeter, a voltmeter, and an ohm meter. And an ohm meter is just a tool to measure resistance. And let's actually do that. Now, to do that, there's a few things we have to do. With a multimeter, because it has multiple functions, you have to set it to the right function. So in this case, we'll set it to ohm meter. And then this is very important. When you're measuring resistance anywhere in the circuit, you need to make sure that the power is off. And unless you want to chase your own tail all day long, you want to isolate what you're measuring from the rest of the circuit. So then we'll actually take the leads and we're going to see the value here. And remember we did the math of this being something like 8.3 ohms. Well, we're getting about 1 ohm right now. And that's not wrong, actually. The thing with light bulbs is they have very little resistance until they heat up. In fact, many kinds of loads exhibit different resistance when measured without working current, motors being another good example. But we can still trust Ohm's law to tell us what the resistance is under load, as long as we know the voltage and current. So then, what do the ratings on this light really mean? Well, most loads are rated for a certain voltage, but in the end, what the manufacturers know is that with those voltages, the loads will allow for the right amount of current to pass through. Okay, so what happens if I power this 2.5 volt light with more than 2.5 volts? Following Ohm's law, as we increase the voltage, the current also increases, making the light brighter. But remember, this is creating more heat, and eventually this burns out the filament. Notice now that there is zero current flow through the circuit. The filament in the bulb has actually split into two, and if we measure the resistance of the bulb now, it's infinite. Using Ohm's law, infinite resistance equals zero current flow. Makes sense, right? Lights aren't the only resistive loads out there, though. Heating coils on your toaster, for example, are resistors where almost 100% of the energy is dissipated as heat. And then there's also resistors for the sake of resistance. They dissipate heat, but that heat isn't necessarily put to use. When I first encountered these, I asked, why the heck would anybody want to use something like that? And there's a good answer that'll take just a minute to get to. Let's assume that we're set on using a 2.5 volt light on a circuit with higher voltage. How do we get away with that? And can we get away with that for more than a couple seconds? The answer is yes, using a series circuit. A series circuit is a circuit where we have 2 or more loads connected end to end like this. The first thing you'll notice is that when we supply 2.5 volts to this circuit, the current flow is decreased from our original 0.3 amps. And the lights are so dim, it's hard to tell they're even on. This tells us that as we add more loads or resistance in series, these resistances add up, resulting in decreased current flow through the whole circuit. So let's see what happens if we increase the supply voltage to 7.5 volts. Now the lights are shining brightly, and the current flow has increased to 0.3 amps, the sort of sweet spot for these lights. What's really happening is each one of these lights is taking a portion of the supply voltage. And since they're all the same, they're each drawing a third of the voltage, so 2.5 volts. You can confirm this using the voltmeter function of a multimeter, showing close to 2.5 volts. You'll also see that if we remove any one light in the series circuit, current stops flowing through the whole circuit and all the lights go out. To find out why all this happens, it's helpful to look at a water analogy again. We can start out with a hose in a single restriction. The water flow is pretty high, but now if we add another restriction, there's more pressure drop and the flow decreases. Add another and it goes down even more. So each restriction adds onto each other. The water flow is the same throughout the hose. It's not like there's more flowing through this restriction than this one, it's all the same. Then if we add a restriction that completely limits the water flow, there'll be no flow through any part of the hose anymore. The same goes for series electrical circuits. Resistances add on to each other, but since they're all sharing a common conductor, the amount of current flow through each resistor is the same. Voltage is dropped across each load, proportionally to its resistance. And when we add up these voltages, they're equal to the total voltage of the circuit. If we remove one load while keeping the supply voltage the same, the result is that the 2 remaining lights will each take half of the supply voltage. And because our total resistance is now lower, the current through the whole circuit increases. In the case of the lights, they're all the same, so they all behave the same. So let's take a look at a series circuit with different resistances. And for this, we can go back to our original query. Let's try to use a single 2.5 volt light in a 7.5 volt circuit. And that's where these otherwise useless resistors come in. We could add one in series with our single light, and if we can get it to take up or drop 5 volts, then our light would get the remaining 2.5 volts, which would be perfect. To find out what size or how many ohms of our resistor to use, we use Ohm's law again. Resistance equals voltage over current, so knowing that we need to drop 5 volts across the resistor, and we want 0.3 amps across the resistor and the whole circuit for that matter, our result is roughly 16.7 ohms. So I've actually made this circuit, and I'll use my voltmeter to verify the voltages. You can see here that we do in fact drop around 5 volts across the resistor. Then if we measure the light, we're right around 2.5 volts, so that's perfect. The resistor I used is what you'd call a fixed resistor, as in it's always the same resistance. But here's an example of a variable resistor or rheostat wired in series with the light. As we move the rheostat, we're changing its resistance and thus changing the resistance of the whole circuit. This allows for more or less current to flow through the circuit, thus changing the brightness of the light. To me, this is one of the most dynamic yet simple demonstrations of Ohm's law at work. Old Christmas lights and even some new ones are wired in series. You may have 60 lights in series in a 120 volt circuit, meaning each light would drop 2 volts across it. This works great, except if one single light goes out, the whole circuit stops working. So what's the alternative? It's parallel circuits. A parallel circuit is one in which the loads are arranged in parallel loops to one another, just like this. The first thing you'll notice is that at the original 2.5 volts, as we add lights, they remain nice and bright. And the more lights we add in parallel loops, the more current the whole system draws. This tells us that as we add these loads in parallel, the overall resistance of the circuit decreases. Furthermore, if we measure the voltage drop across each light, it's the full 2.5 volts coming out of the power supply. Are you confused yet? Well, watch this. As I remove light bulbs to simulate a bad bulb, the other ones stay lit, no matter which one I take out. Let's represent parallel circuits with water. I've got this water manifold with different paths for water to flow through, and right now I'm only allowing one of the paths to flow just a little bit of water because I have a pretty good restriction here. But if I open up another path on this manifold, more water can start to flow, and now we have twice as much water. And if I open more, we have even more flow. The more paths we allow the water to flow through, the least the overall resistance it encounters, and the higher the overall flow. Of course, if we open up one of the restrictions, more water will flow through that path. And if I close off any path completely, the other paths don't really care. They'll keep on flowing just the same. Electrically, again, we're dealing with the same thing. As we add more parallel loads, they're actually giving the current more paths to travel through, meaning the total resistance of the circuit decreases. As a general rule, the total resistance obtained by this equation will always be lower than the smallest resistor in our circuit. And because the resistance is lower, the total current flow is therefore higher, with each parallel branch making up a portion of the total current flow. Meanwhile, the voltage across each load is exactly the same. That's why each light stays lit nicely. We're no longer sharing the voltage like we did in a series circuit. In this case, we had the same load across each branch. But let's see what happens if we use different loads. We've got 3 resistors here, a 2 ohm, a 4 ohm, and a 10 ohm one, wired in parallel with a 12 volt battery. Because it's a parallel circuit, we know that each resistor will receive or drop 12 volts. So we can easily do the math and find out that the current going through each load is different. Another thing we can do is find out the total resistance of the whole circuit in a few different ways. We could use this equation to find out the total resistance. If we plug in the values, the answer is 1.176 ohms. Another way to get there is we'd already figured out the current flow for each branch, so we could just add that together and get our total current flow, and then use Ohm's law to obtain the resistance. And of course, the numbers match, and that's one cool aspect of performing circuit analysis. There's often different ways to reach the same answer. Now, series and parallel circuits can also be used with batteries. Volta's pile was nothing but a bunch of battery cells stacked in series on top of each other to increase the voltage. Your remote control, for example, uses 2 1.5 volt batteries connected in series, making the total voltage 3 volts. So when you go to jump a car battery, you always want to connect it in parallel, positive to positive and negative to negative. What you're actually doing in this case is increasing the capacity of the battery. If you were to connect it in series instead, positive to negative, you'd be doubling the voltage and most likely burning a bunch of fuses, so don't do that. A little bit earlier we talked about Christmas lights, and I want to show you one more configuration. As you can see here, we've got these lights wired in series, but if we zoom back, we can see that this series circuit is actually part of a parallel circuit. It's just one branch of it. So we can actually combine the two types of circuits into a complex circuit, or series parallel circuit. This can have many advantages, like here if a light burns out, we only lose those few lights. Or here we have the opposite, a parallel circuit within a series circuit. And if you think about your house wiring, we have all these parallel circuits that you may choose to plug into and create even more circuit complexity. So with all this complexity, we should start talking about ways to control electricity. And for that, we go into the next chapter.
Has this ever happened to you? Let your appliances turn on and off just by clapping. Clap on the music.
Oh, the 80s. While controlling a circuit by clapping isn't really what this video is about, inside that device is a switch. And believe it or not, switches have completely revolutionized electricity. This here is a very rudimentary switch. All it does is control whether electrons can flow through the circuit. If the switch is closed, current flows. If it's open, current can't get from here to here, so it stops flowing. And before I go any further, I want to mention that up to this point, we've been getting away with using these nice illustrations to show circuits. But engineers and technicians don't use anything like this in practice. Instead, they use schematics or circuit diagrams, which are universal symbols representing different components within a circuit, like a battery, a light, a resistor, or a switch, the same one we were just using. Within our circuit, it would look like this. This switch has two positions, on and off, and it controls only one circuit. We can refer to this as a single pole, single throw switch. Some switches can control multiple circuits or have multiple positions. In switch terminology, the number of poles is the number of separate circuits the switch controls, and the number of throws is the number of possible output connections that can be made. Switches can also be normally open or normally closed. For example, a push-button switch may only close temporarily when pushed, making it normally open as that's its default state. Now, switches are designed to handle a certain amount of current and voltage, and one issue they encounter with higher voltages and currents is possible arcing. As we close the switch, high voltage or current can bridge the air gap before the contact is made, wearing out the contacts and eventually rendering the switch unusable. This is just one reason why faster electromechanical switches are used. To understand how they work, we first need to have some fun with magnets. Let's take a couple steps back and ask, what is a magnet anyways? We already talked about how like-charged particles like electrons repel and opposites attract. This force exists even if the particles are not in contact, and it's called an electric field. There is, however, a secondary field called the magnetic field, which only exists when particles are moving. If you take a single electron and give it some speed, a magnetic field forms around it. The closer you are to the particle, the stronger the field is. So then, if you flow a bunch of electrons or current in a wire, a strong magnetic field forms around it. You can see this visually by running even a small bit of current through a wire and placing a compass next to it. The compass normally points north, but when we power the circuit, the needle will align with the magnetic field caused by the current moving through the wire. A former British soldier and shoemaker named William Sturgeon harnessed this very concept to create the world's first electromagnet, to the delight and joy of 8th grade science teachers everywhere. You've probably seen the science experiment before, where you coil some wire around a nail and it becomes an electromagnet. All we're doing is taking the magnetic field created by the current flowing through the wire and amplifying it by wrapping the wire. The nail then becomes a polarized magnet with a north and south pole. But what about magnets that don't require electricity, like the ones in your fridge? Permanent magnets work in a slightly different way. Remember the orbits around the atoms? They're not actually always circular like this. They can take on many different shapes. As electrons move around these odd shapes, they create magnetic fields because, well, they're moving. In most atoms, these magnetic fields tend to cancel out, but elements like iron are a bit different. Due to the number of electrons on the valence shell and some other quantum physical phenomena, not everything cancels out perfectly, and we're left with an atom that has a small asymmetrical magnetic force. Basically, a tiny, tiny magnet. If enough of these atoms line up into magnetic domains or chunks, they create a slightly bigger magnetic force, and if enough of these chunks line up, they create a usable magnet with a common north and south pole. You can even see the magnetic fields around these permanent magnets if we just pour some iron filings over them. But we have to be careful here. The lines only appear as lines because the iron filings like to stick to themselves. But there's actually an infinite amount of possible lines since it's a field. So if we go back to the electromagnet, the iron nail in the middle actually becomes a magnet when current is applied because the little magnetic domains in the iron align with the magnetic field induced by the wire. The result is very similar to a permanent magnet, but as soon as we turn the electricity off, the magnetic domains revert to their original position, and the nail is no longer a magnet. And this is an important fact, which takes us back to our original question of electromechanical switches. Solenoids, relays, and contactors are all kinds of electromechanical switches, and they work on the same basic principle as the wire wrapped around the nail. Imagine we have a load we want to control. In the case of the relay, we have an electromagnet with a static ferrous core, like the nail. When we energize the coil, the resulting magnetic field moves a mechanism that opens or closes a contact. So it's basically a switch, just controlled a different way. And solenoids and contactors do something very similar but are designed to handle much larger loads. But how are these different than a switch other than being pretty fast? Well, notice that the circuit used to control the relay or solenoid or contactor is separate from the circuit actually energizing the load. This can be a huge benefit. It may only take 1/10 of an amp to power up this electromagnet, while the load is controlling takes 10 or 100 or even more. To visualize this, let's take the starter in my awesome minivan for example. It takes about 150 amps of current to start the engine. To receive this much current, the starter needs these huge, heavy cables. If all we used to energize the starter was a manual switch, we would have to route these cables into the interior, and then we'd need a huge switch to control it. This would not only be expensive, heavy, and ugly, it'd be outright dangerous. So instead, cars use solenoids to keep all the high current in the engine bay and control the starter from a distance, with smaller wires that only carry that current needed to energize the coil. Notice that in this case, we're using a manual switch, the ignition switch, to control the electromechanical device. Using switches to control other switches really opens up an entire world of possibilities. Check out this bell here. This arm is controlled by the relay. So if we energize just the relay, we get one ding of the bell. I could sit here and flip the switch back and forth and it sort of sounds like a bell, not really. But look at this ingenious mechanism built in. If we instead connect the circuit like this, current will first pass through this arm, then make its way to the relay. As the relay energizes, the arm would move down and hit the bell. But as soon as this happens, it opens up this contact here and opens the circuit, which stops the flow to the relay. And the arm comes back again. As it comes back again, the arm makes contact here, sending current to the relay and repeating the process over and over again. Here's what it looks like at full speed and in slow motion. Pretty cool, right? Later on this video series, we'll expand on this idea of building complexity out of switches, which will take us all the way into the world of electronics and logic. But before we get there, with great power comes great responsibility, so let's spend the remaining few minutes of this video focusing on safety. This is a circuit breaker. You'll find many of these behind the circuit breaker panel at your house. A circuit breaker is essentially a switch designed to open a circuit and stop the flow of current when there's an overload. Because homes are wired in parallel in this configuration, the more loads you add, the more current will flow through the circuit. But look at these two wires. They have to handle the entire current flow of the whole circuit. And that can be a problem when dealing with increasing loads. Wires are rated to handle different amounts of loads. Pass too much current through a wire and it will heat up, just like the filament in a light bulb. But why? No material is a perfect conductor, and wires do have some small amount of resistance. Generally speaking, thin, long wires are bad at carrying a lot of current. Think about it. We've got all these electrons trying to flow through this conductor, and the copper structure becomes a bit of a bottleneck. So they keep hitting the copper ions as there's just not enough room. This creates heat, and the longer the cable, the more voltage is lost due to the added resistance. An extreme example of this is Volta's accidentally glowing wire. You definitely wouldn't want the wires in your house to get red hot or anywhere close to that. For this reason, the American wire gauge standard was created all the way back in 1857 to specify the right diameter wire for the expected amount of current. Somewhat against intuition, they labeled the larger diameter wires with smaller numbers, and small wires with large numbers. I did some research about this, and it's because of how wires were made back then. You'd start out with a pretty thick wire, and then you'd pass it through a die and stretch it. For a size 8 cable, you'd stretch it 8 times. For a size 14 cable, you'd stretch it 14 times, and so on. For economics, we specify the smallest possible wire that will still handle the expected load. For most applications, that expected load is often 15 or 20 amps. But then what if we go over this? This is where circuit breakers or fuses come in, as a means of protecting both the wires and the loads from too much current draw. The difference between a circuit breaker and a fuse is that a fuse just goes bad or opens when overloaded, while a circuit breaker trips but can be reset. I've actually taken apart this 15 amp circuit breaker so we can visualize this. When set to on or close, there's a path for the electricity to conduct through the circuit breaker. So in this setup, we have a space heater and a heat gun, and together they draw just over 21 amps. But you can see the circuit breaker is not tripping yet. As time goes on, the wires carrying this current are definitely heating up, but so is a tuned thermal element inside the circuit breaker. Here you can see it slowly moves as it expands. Eventually, this movement is enough to release a trip mechanism, which opens the circuit breaker and turns off the appliances, protecting the circuit from all that excess heat. This is what's called a slow trip. There is, however, another type of overload called a short circuit. It's called a short circuit because somehow the wires make a connection, creating a new shorter circuit and typically bypassing the loads. If we look at Ohm's law, you can see that with basically close to zero resistance, the current flow will be almost unlimited. Unless you were looking to start a bonfire inside your walls, that's a bad thing. If this were to happen at your house, the circuit breaker would be designed to open the circuit as fast as possible, experiencing a fast trip. To demonstrate this, I've created a short circuit which is close by this switch. You can see that as soon as I flip the switch, the circuit breaker trips almost instantaneously. This time though, it's an electromagnetic element inside the circuit breaker that triggers the mechanism due to excess current. The end result being, again, circuit protection. So clearly here for the video I have staged this short circuit, but how does this happen practically? Well, wires can rub their insulation layer off and make contact with each other, mice can chew on wires, loose connections could give out and cause wires to touch, connections could be exposed to water, and devices could have internal faults causing shorts. Let's look at this last one a little bit more. Say we have a microwave which runs at 120 volts. Just like with all of our examples so far, we've got two wires which carry the electricity through the circuit. And yes, I know it's a bit more complex than that since this would be alternating current, but we'll focus more on that on the next video. The outside frame or chassis of the microwave is made of metal, and in this scenario, after some time, one of the power cables has rubbed its insulation and is now making some contact with the frame. We would say here that the wire is shorted to the frame, and this would be a very dangerous situation, as the frame would be at 120 volts of potential. That's a bit like leaving an exposed cable that someone is very likely to touch and get shocked. So you may have noticed that a lot of devices have a third connection, the ground terminal, which connects to the wall. This ground is a crucial safety feature, and in essence, it's a cable that ultimately connects the frame of the appliance with the neutral cable, or the cable through which the current is returning to the source. Under normal circumstances, there would be zero current flow through this ground wire. But like in this case, if a cable was shorted to the appliance, instead of just hanging out and leaving the frame at 120 volts of potential, which could be deadly, the current would take the path of least resistance through the ground wire and flow around the load. Since the resistance through this ground wire would be so low, the current would be very high, but only momentarily, as that high of a current would trip the circuit breaker and that would stop all current flow. With this kind of protection, the potentially fatal situation is stopped immediately. And even if you try to reset the circuit breaker, it would open again, so anyone around the appliance would stay safe. Now, there are other types of faults like ground faults that we can also protect against, but since we haven't talked about AC current in detail yet, I'll leave that for the next video. But the last thing I do want to talk about is a safety issue that we can't really safeguard against, and that is bad connections. Here I have a small motor controlled by a switch, and this motor is designed to run at 3 volts. Now, as we look at this circuit, we can kind of assume that with the switch closed, the switch is acting just like a wire. There should be no voltage drop across it, so the motor gets the full 3 volts. But what about if the switch is worn out and isn't making a great connection? I will simulate this by not fully closing the switch and watch what happens to the current in our circuit. It drops. You can even hear the motor running slower. Using Ohm's law, we know that at the same voltage, if the current drops, then the resistance must have increased somewhere in the circuit. So taking my meter, I can see that we now have a voltage drop across the switch itself of around 1 volt, meaning our switch has effectively become a resistor. And that's not a great thing. All that resistance is creating heat, and the switch isn't really designed to dissipate that heat. As we deal with larger voltages, creating resistance in a circuit where there's not supposed to be one can be problematic. Let's demonstrate. Here I'm drawing about 20 amps again through the space heater and heat gun. And I've purposely made this connection weak and loose. Watch what happens over time as we continue to draw current. The excess resistance is generating heat. So much heat in fact that it's even melting the insulation. The appliances of course continue to run and eventually this connection starts to glow from the heat. You can imagine that, even if this happened inside an electrical enclosure, the potential for fire is still real. This is something to keep in mind whenever making any connection. Throughout the whole process, we could introduce added resistance, whether it's stripping a cable and leaving lots of marks on it, crimping a connector poorly, or failing to properly tighten a connection at a terminal or bus. At the end of the day, electricity is just physics and chemistry, and it will consistently follow the laws of nature. Having a better understanding of the fundamental concepts that govern these laws can make you much more effective at interacting with and designing electrical systems safely. In the next video, we'll be taking an in-depth look at alternating current in all its flavors, what it is, how it's generated, how it compares to direct current, and how we can convert from one to the other. This will take us into a deep dive into motors and motor controls. Later in the series then, we'll be discussing logic from its base level to full integration. So stick around to keep learning these fundamentals with us.